Now, under the topic reformulation, we are going to study a new theorem, which we have not studied in the previous chapters. It is the real valued function. The real valued function f is continuous at the point A in R if and only if whenever sequence xn is a sequence, it's a sequence of real numbers, converging to A, then the sequence f of xn converges to f of A. That is, f is continuous at A if and only if whenever there exists a sequence xn converging to A, then the sequence f of xn should converge to f of A. This is if and only if this condition is satisfied, then f is continuous at A. If f is continuous at A, then whenever a limit sequence converges to a point, then the corresponding functional value sequence also converges to f of A. We have to prove this one. We have to prove the necessary part as well as sufficient part. So now we will prove the necessary part. It is, we will assume that f is continuous at A. We will prove that whenever there is a sequence xn converging to A, we have to prove that f of xn sequence converges to f of A. So first we shall prove the necessary part. Okay. Now first let us assume that a function f is continuous at a point A. In R. And we have to prove that if sequence xn converges to A, then f of xn sequence converges to f of A. Now, so that we assume one thing, that is, let us assume that there exists a sequence xn be any sequence of real numbers. Suppose there exists a sequence of real numbers converging to A. And if suppose there is a sequence of real numbers converging to A, the meaning is there exists a n such that whenever n is greater than or equals to capital N implies xn minus A is less than epsilon. So that is, after this capital N, the elements comes very close to what? The sequence element comes very close to A. So except the finite number of values, that is x1 to x capital N minus 1, that alone will be very far away from A. But after that, infinite number of sequence elements comes very close to what? A. So what happens is, if this is the case, and since f is continuous at A, so we f of x1, f of x2, everything is defined for sufficiently large. So that's why. So now we must show that So we must show that the limit of the sequence f of xn equals to f of a. That is, for given epsilon greater than 0, we must find n in I such that f of xn is element of the open ball b of f of a colon epsilon. That is, what is the meaning of this using the definition? For a given epsilon greater than 0, there exists a n in I, such that whenever n is greater than or equal to Kaplan, f of xn and f of a, the distance is less than epsilon. So this one only I have written in terms of open ball. That's all. That is a new formulation. No? We are studying. We have formulated the definition newly in terms of open balls. So f of xn must be element of this open ball whose center is f of a, radius is epsilon. This is what we have to prove it. So I give this one as 1. We need to prove this one. But it is given that, but f is continuous at a. It is given. It is assumed. Sorry, it is the assumption of the necessary part. This is the assumption. You see, in the necessary part, what we assumed, f is continuous at a. So f is continuous at a. Therefore, the same epsilon, I am going to find a delta. Therefore, for epsilon greater than 0, there exists a delta greater than 0 such that whenever x belongs to the open ball, a colon semicolon delta, then f of x belongs to the open ball, f of a semicolon epsilon. Okay, this is by the definition, assumption of the necessary part, and I am using the definition of continuous function. This one we give the number 2, this result. Furthermore, since we have that limit n tends to infinity xn equal to a. See, under the necessary part, this is one assumption. The other thing is, we assumed that this is also true. If this is true, we have to prove that this result is true. So furthermore, since xn approaches a, there exists a n in I such that whenever n is greater than or equal to Kaplan, my xn should fall in the open ball whose center is a and radius is delta. So here, for this sequence xn approaching a, instead of epsilon, we use the see here to understand more clearly. I write like this: for a given delta greater than 0, okay, there exists a n in I. So I can write like this. Instead of epsilon, I use the word delta. That's all for this definition. So now, whenever n is greater than or equal to Kaplan, I get xn belongs to this open ball. This is result I named as 3. So now I am going to relate now 1 and 2. So I get 2 and 3 I am going to relate it. So now for this n, therefore for n greater than or equal to Kaplan, we get xn belongs to the open ball A colon delta from 3. And if x belongs to this open ball, then what I get? This implies that f of xn belongs to the open ball f of a colon epsilon. This is from 2. See, the thing is, generally we write it as x. So, so here I put xn. That is also an element. Okay. So when x belongs to this open ball, f of x belongs to this open ball as per 2. So from this implies this. That is from 2. So now, therefore, just you can combine this and this. Therefore, so what we proved so far is, therefore, for given epsilon greater than 0, there exists a integer n. So we found that n. This n is existing. Sorry, this n, capital N. This n is such that whenever n is greater than or equal to capital N, n is greater than or equal to capital N, this implies that f of xn is belonging to what? The open ball f of a colon. That is what I have to prove. That is what 1. See. Sorry, 1 here. So, for a given epsilon, we must find a ni such that whenever n is greater than or equal to capital N, we have to prove that f of xn belongs to this open ball f of a colon semicolon epsilon. So we proved it. Hence the necessary part. So what we proved is, one part of the proof is over. That is, if f is continuous, we have assumed it. We have proved that if the sequence xn is converging to A, we have just now proved that the sequence f of xn converges to f of A. Now we are going to prove the sufficient part. That is, we will assume that this result is true. We are going to prove that f is continuous at A. And now we are going to use contrapositive technique for proving the sufficient part. Okay, now we are going to prove the sufficient part. Okay, the sufficient part we are going to prove it. Suppose I assume that limit the sequence xn has a limit A implies the limit of the sequence f of xn converges to f of A. We need to prove that f is continuous at A. That is what we are doing. Now, if f is not continuous, we are going to assume the contrary. Suppose, let us assume the contrary, that f is not continuous at A. So now you see, I am going to use the definition continuous function in terms of inverse functions. So what I have defined is the inverse image of any open ball whose center is f of A and radius epsilon contains the open ball with center A and radius delta. That is, for given epsilon greater than 0, where exists a delta greater than 0 such that this is true. Okay, This is also a definition of a continuous function. Continuous function f at a. So for a given epsilon, there is a delta such that the inverse image of the open ball center at f of a, radius epsilon, contains the open ball whose center is a and radius is delta. So I can find that kind of open ball, delta I can find it. So this is what it says. So now suppose I assume that f is not continuous. So how can I define this one in terms of inverse function? So any given epsilon I can find one delta such that the inverse image of this open ball always contains this open ball. So what is the converse of this is? If this is not true, so what happens? So therefore for some epsilon greater than 0, for some epsilon greater than 0, the inverse image of inverse image under the function f of b, which is f of a colon epsilon, contains no open ball, contains no open ball about a. So whatever epsilon real number I give, positive real number, I can find one open ball like this such that the inverse image of this open ball will contain this open ball. So what is the converse of this? There exists at least one epsilon greater than 0 such that the open ball, the inverse image of this open ball contains no open ball about it. Does not contain open ball means what? It is not this open ball is not completely inside this open ball, this inverse image. Already I explained, now I will just go back. Yes, here the inverse image of this is this bigger one. That bigger set should contain this open ball. So what is this? We have assumed that f is not continuous, so this should not happen. So there exists one open ball whose radius is epsilon such that the inverse image of this will be something like this. I will write and see in red. No open ball with center at A is completely inside this inverse image, the blue color one. That is what we have assumed it. Because f is not continuous, so there exists one epsilon such that the inverse image of this kind of open ball will not contain any open ball whose center is at A. So if you understand that concept, you can just see here, contains no open ball about A. In particular, f inverse of B does not contain any open ball about A. That inverse image will not contain completely. So it does not contain an open ball whose center is A, radius is 1 by n. No open ball about the center A will be inside that inverse image. That is what this statement says. So definitely this open ball whose center is at A, radius is 1 by n. This is true for any n. So all these open balls, suppose n equal to 1, n equal to 2, n equal to 3, all the open balls, same center, it will be like this. Radius 1, center is A, then radius 1 by 2, that open ball will be like this. Next, radius 1 by 3, the open ball. All these open balls, we write it in a single statement like this. So there are many open balls. All these open balls will not contain what? Will not be inside this B of f of A colon semicolon epsilon. So thus for each n in I, there is a point. If it is not completely inside one set, what is the meaning? There is at least one point that is outside what? This B of f of a semicolon epsilon. So there exists a point, say at least one point, xn belongs to B of a colon 1 by n, such that f of xn is not an element of B of f of a colon semicolon epsilon. That is a mean. See, this open ball, all these open balls are not completely inside also open ball. See that this is a rough side. See this one, domain. See, this is the open ball whose center is f of a and radius is epsilon, and call this as my open ball called as B of f of a semicolon epsilon. The inverse image of this open ball, somewhere here I name this open ball as B, A, whose radius is delta. I name this open ball as B of a colon delta or anything. Suppose I think general open ball. So the inverse image of this open ball under F, what we assumed is that does not contain this open ball completely. This inverse image. This one I am going to give it as F inverse of B of f of a semicolon epsilon. Okay, so like this. So what we have assumed so far is the inverse image of this open ball will never contain any open ball whose center is what? Whatever open ball you take whose center is at A will not be completely inside this inverse image. That is what yes, that's what this says. For some, the inverse image under F contains no open ball about E. This is what that sentence says. No open ball about A will be completely inside this inverse image. Okay, so now what we have assumed is, like this I have created many open balls whose center is A, the radius is keep on changing, that is reducing. So all these open balls will not be completely inside this inverse image. So from each of these open balls, that is, there are many open balls. That is, the first one is B of A colon 1, next B of A semicolon 1 by 2, next B A colon semicolon 1 by 3. It goes on like this. Infinite number of open balls. All these open balls, the center is A, but radiuses keep on reducing. All these open balls will not be completely inside this inverse image. So what is the meaning? There exists at least one element in each of these open balls that is not inside F inverse of this. That is what we needed. So like these elements I keep on taking it and I am going to collect them. Okay, so if suppose this is one open ball, I take one element here, definitely the function value of this will not be inside this, because the inverse image of this is this. So if any element is here, that corresponding image will be inside this. If the element is outside this inverse image, it will not fall here, it will somewhere here and here. So that concept I just want to explain you. So now I go to the proof. Okay, so now this is not needed, just for visualization. So now Thus for each any knife there exists a point xn like this. One point I take, that xn belongs to that particular open ball, which is not completely inside this one, but if you take the function value, what will happen? That function value will not be inside this open ball. Okay, that's what I explained. So like this, if you keep on doing like this, that is, what I say is, whenever xn is very close to A, so what is the meaning of this is, xn is belonging to the open ball A colon semicolon 1 by n. This is the meaning of this. If I take an element xn belonging to this open ball and the corresponding function value is not inside this open ball, so what is the meaning? If it is outside this open ball, so what is the meaning is, the distance between f of xn and f of A must be usually less than epsilon, mean it is inside that open ball. So now I am going to write this is greater than or equals to. So this implies that, so this is a contradiction to our assumption that, what is the assumption we made in the sufficient part? We assumed that whenever x is coming very close to A, f of x must come very close to f of A. But here what happens? Here what we got it is, we are coming very close to, xn comes very close to A, but f of x is not close to f of A. We are getting greater than or equal to epsilon. So this implies a contradiction to the limit of the sequence f of xn converging to what? F of A. Therefore, our assumption is wrong. What is the assumption? F is not continuous at A is wrong. Therefore, f is continuous at the point A. Hence the sufficient parts, and hence the theorem. It's a sufficient part and hence the theorem. Okay. So we shall stop here. Thank you.